This question reads, water flows from a lake into a turbine that is a vertical distance of 90 meters below the lake as shown. The mass flow rate of the water is 2,400 kilograms per minute. The turbine has an efficiency of 75%. What is the output power of the turbine? I kind of want to anchor my thoughts on efficiency, right? So give us the efficiency. So let's remind ourselves that efficiency is the useful. Now, since all of our answers are in power, we could define efficiency in terms of either energy or power. Let's just sort of begin with the end in mind. So the useful power out over the total power in. And they're saying that that's only 0.75. Okay, so the ratio of how much useful power we're getting out to the total power that goes in is only 0.75. They want the output power. So we're solving for the numerator here. So it's kind of nice. We've got the quotient, the ratio, and there must be a way to figure out the denominator, right? Because it's asking us about the numerator. So that's why it's nice to just sort of anchor your thoughts on an equation, because even if it's not clear at first, how to approach the problem, it at least gives you sort of a roadmap. Like, at least I know what I need to do now. I need to somehow calculate the total power that went into this. Well, how am I going to do that? If we consider this figure, it's like, where's the energy coming from here? This 90 meters is a clue. I'm going to call it H for height. Okay. Now there's a mass flow rate. Okay. The per minute is what's going to turn energy into power, right? Because we know that power is the rate that energy is converted. And so what we have here is some potential energy due to gravity with all the mass of water that's in this lake that's 90 meters up above the turbine. So there's energy equal to mgh. Now, what we're given here is a flow rate. In other words, to turn energy into power, as I just mentioned a moment ago, we've got to divide by time, right? It's the rate that energy is transferred. And so a way to turn this potential energy into, the power is to realize that we're given the mass per time, right? So we could divide the energy by time to get power. They give us the flow rate, right? So they're giving us the mass per unit time, but the unit of time they give us isn't, the SI unit. So there's no way we're going to get watts or kilowatts or megawatts out if we leave our time in minutes. And so a good first step here, in other words, we want to substitute this value in for m over t, m over t right here, the mass flow rate, because we know G is 9.81 here on Earth, and we're given H equals 90. So we have everything we need here. We just have to kind of, clean it up a bit. 2,400 kilograms per minute. And I just looked it up in a textbook, there's 60 seconds per minute. So that's kind of information that you can readily find in the literature. Or maybe you've memorized it by now. All right, so we have here 40 kilograms per second. If you're getting 2,400 kilograms in a minute, that's 40 kilograms every second. So there's our mass per time, 9.81 newtons per kilogram is another way to, meters per second squared, the acceleration due to gravity or the gravity field strength in newtons per kilogram, force per mass, and then the height here is 90 meters. So when we multiply this, what are we going to get? We're going to get kilograms canceling. We're going to get Newton meters per second. A Newton meter is a joule, and a joule per second is a watt. So this will give us the total power in the denominator here. 40 times 9.81 times 90 gives us 35,316 watts of total power. That's the total power that goes into the turbine. If all of the energy were converted, that's how much we would get out. If this were 100% efficient at converting the potential energy into, electrical energy, then we'd get all of that out. But we don't. It's only 75% efficient, right? So we substitute this in for the denominator, and we're solving for the numerator. So we got something now that looks like the power that we want to solve for, right? The power out, the POUT, over 35,316 equals 0.75. So if I multiply 35,316 by 0.75, I get 26,487, which is pretty close to 26 kilowatts. And so we were hypothesizing earlier, just throwing out wild speculation, C, B, just any answer. Okay, just to hold up a hypothesis, just to disprove it, just to revise that hypothesis for good practice of the scientific method. So at this point, we'll revise our hypothesis and say, yeah, 26 kilowatts seems like the best answer here based on that calculation.